Hello, my name is Nico Punt, and in this video I'm going to demonstrate the basic workflow in KinPop++, the population modeling module of the Edsim++ application. So what are the entities we are dealing with here? So of course we have the KinPop++ module, and we can have two data sources. The first data source can be MW Farm, the TDM software application, or it can come from a database within the hospital information system. So what does KinPop at least need as an input? And that's a series of EDX data files in the project folder. And there are two ways to obtain those EDX files. First, they can come from MW Farm++, where you can go to the extract screen, where you can do patient extraction, and this will directly generate these required EDX files. If your data is coming from a database in the hospital information system, you usually do a database query and then accumulate your data in an Excel spreadsheet. And then you can import this Excel spreadsheet in Edsim++ using the file merge patients command, and then you also have the required EDX files in the project folder. Well, these EDX files are not, let's say, the population model you are going to analyze. These EDX files are just used for capturing the data. So it can be some very simple model. As long as all required variables are defined there, you can use that simple model to capture the data. So once we have the data in the project folder, we load our EDX population model, so the model we want to analyze with that data. And what happens is that during the process, the data contained in these data files are copied to the population model and duplicated for each patient. So when we're done with analyzing, we will typically generate a report by clicking the X button, and then you also get a Excel spreadsheet with all the output. So let's focus for a moment first on the route from MW Farm in the patient data extract screen. And in order to demonstrate that, I will log into the MW Farm. And there's no need to load a patient. We can directly go to the extract screen. And what you see in this screen is just a list of all patients in the database. And what you can do is limit the number of visible patients by applying certain filter criteria. So for a particular drug, for a particular gender, an age range, body weight range, or a range of creatinine levels. You can also enter a value for tag, which corresponds with the with text in the pathology field of the status screen. So I can now select or deselect patients by selecting a patient and clicking the toggle button. And you can do the same thing with the spacebar, and you can use the cursor keys to navigate the selection. So here you see already a pre-selection, a default selection, and this is a group of patients that was participated in a study of for tobramycin, and these were an ICU population. So I could now click the extract button to extract the data, but first we must set an output directory, so our project folder. So I click on the two dots here, and I will select a different output directory. I have some older ones right there. I will delete them because we're going to recreate them. Okay, so I'm going to make a new data directory, and I call it my data. And select it. You can see it directly here, my data. So now I can click on extract. The progress is shown in the progress bar here. So now the data is already extracted, and we can directly explore the data by clicking explore here. And you see here those individual EDX files. You see here an additional file, and it's an Excel file, and it's the same kind of Excel file you would create if you wanted to import this into the Edsim++. So what I will do is I will copy this file, go up one level, make a new folder, my data 2, and paste this Excel file. So please note that there are no EDX files yet here, but we come back to that later. Okay, so what we now want to do is demonstrate how you go about in Sin++ and KinPop++ with these data. So I'll close this. I close this, the MW farm. So let's continue with the presentation. So I just now demonstrated the patient extract. So the alternative would be that you do get a query from the hospital information system database and get this Excel file. And what I just did is I made a copy of this Excel file I just exported, and I will use this Excel file as an example. So we're now going to go to AddSim and select File, Merge, Patients in order to generate these EDX files in the project folder. Okay, so I'm right here, and first I have to, of course, select a model where to store the data in, and this can be, as I said, a very simple model. I will simply use the same model which was used to capture the original data. So I will take this one. So I have here a model which I'm going to use as a data carrier, and now I select File, Merge, Patients, and I go to Mediware Datasets. So, and then I select My Data 2, and I select the Excel file. So now the data is already imported, and let's see if we can check this. So I will open the file manager again. Let me see. There it is. Look at C, Mediware, Dataset, My Data, and here they are. So here the EDX files are generated. So now we have demonstrated those two routes to get those EDX files. Okay, so what's next? So the next thing is that we're gonna have we're going to open the population model we want to analyze, and we select the project folder, and then we can start the analysis. So I will go here and I will now open the file. I could use this file, of course, as a population model, but I prepared already somewhat earlier. If you go to EDX and then go to KinPop and PAM, I have a demonstration. So it looks very familiar, but some of the parameters are already set. And now I can go to KinPop. I can select the proper project directory again. So that was My Data 2. And you see already the data appears already. So, and I can here, in this moment, I can here already select or deselect patients into this data set if I want to. Now, before I continue, I have to tell a little bit about the different parameter types and error models which you can use in KinPop++. So we have, in fact, with regular normal fitting, outside the context of population modeling, we had these three basic parameter types: fixed, non-Bayesian, and Bayesian. And if we then look at in a population fit context, so you have an individual fit and you have the population fit. So with a fixed parameter type, it's constant, both for the individual fit and the population fits. And for non-Bayesian and Bayesian analysis, there will be an individual fit and also a population fit. But in the population modeling context, we have now two additional parameter types called population fixed base and common population. And so with the common population fixed base, the parameters is fitted for the individual patient, but kept constant for the population. And with common populations, it's just the other way around. Then the individual fit, the parameter is constant, but it is fitted on the population level. So that's important to understand, so we will see this later. And the next thing I want to talk about is the error models. So we discriminate typically between three types of error models. We have the between subject variability. So that's the error in the population model parameters. And then we have the assay error. So it's the error in the analytical procedure, concentrations. And then we have the residual error. So that's the unexplained leftover error, which you also see then in the concentrations. Okay, so let's continue now then with these steps. So I already selected the project folder, I loaded the population model. So let's set up the parameter types and the error model. So I continue here, I go to the settings screen. So here I can set the assay error, and here it's not set, it's 0. And you see different constants, so it's effective polynomial you can specify here. And so the SD0 can be interpreted as the additive error, and the SD1 as a proportional error. Now if I go to the fitting screen, it resembles a little bit the fitting screen you also see in the MW farm. You see here the parameters. So it's the volume of distribution, V1, metabolic elimination, and renal elimination. But you also see here another two parameters called SD0 and SD1. So, and this is the residual error. So if I go back to the model right there, you see here that KinPop automatically added a new object called residual error and added this to the model. And we can enter here, so I entered here these values for the residual error. So, what is now the advantage of using this error model over the assay error is that these values are fixed, and these values, if you want to, can be estimated. But you can have them both. So if you know the assay error, you can enter it here, and then you can combine it with a variable fittable residual error. Again, the additive and proportional factors right here. Okay, so and here we set up the parameters. So we have the volume of distribution as standard Bayesian, and the renal elimination also a standard Bayesian. But the metabolic elimination we use the pop fixed Bayes. And why did we do this? That is because if we look at a data set, there is simply not enough information to account for differences in renal function. So if you then try to fit two parallel routes of elimination, there is very bad convergence because it's indistinguishable. So what we then typically do is to take one of those routes, in this case the metabolic elimination, and set it to pop fixed Bayes. So now we're all set and we can start the procedure. So I click here on start. So after 4 cycles it has been completed, and you see here the value of the objective function for each patient. And the procedure of course will try to minimize the objective function, the total objective function. And you see here one red bar, and this is then an outlier as expressed as the deviation of the objective function compared to the other ones. And we use a special procedure for this, which is explained in the documentation. So what I can do now is look at the output. So if I look here at the log, so this is the analysis log. It says how long the analysis took. You see here the convergence of statistics, so the objective function, log likelihood, Kijker information criterion, and weighted sum of squares. So it at very good convergence. And here the convergation of the population parameters, also very fast. Convergence of the standard deviations and the convergence of the population correlations. The next step we have the the population value. So at cycle 0, so the initial values, this is our initial estimate. And then after 4 cycles, these are the means and the SDs of the population parameters. And you see we have another one, it's called 4C, it's calculated again. And then all population parameters are calculated, even the fixed pop base. So although we set it fixed to 0.1 here, if you then would recalculate it, you would find this value. Okay, this is the values which are relevant right here. Here you see the correlations, the covariances, and some statistics are for each population parameter. And very important then, you see the goodness of fit plots. Here for the individual, so individual predicted versus observed. And then the weighted residuals individual, the weighted residuals in time. And then also for the population. So the population predicted versus observed. And the population predicted versus the weighted residuals, and also again in time. Here are on the patient level details. So this is the patients, list of patients you have, with the number of observations per patient. And here you see the individually fitted parameters for each patient. And you also see, let's say, the a list of observed and predicted. And the last slide, the sim slide, shows you the profile, plasma profile of each patient. You can so this way you can judge how all fits are going. So if you have some deviating patients, you can pick them out from these type of plots. So this is looking all very good. Now, if you have many patients, if you have more than 100 patients, the number of data would be too big here. And so what we do then is that we store an Excel file for each individual patient. With this data you see here with the individual plots, and the plot is now also stored as a picture. So if you then browse the picture with a picture viewer or an image viewer, you can go very quickly, even through a very large number of individual fits. So in the end, of course, we would like to store the data. So if I go back to my fitting screen, I click the X button. And now the Excel output is generated. You cannot see it because it's happening on the other screen right here. I'll show it in a moment. Yes, I'll show it right here. So, and then you have essentially the same sheet. So here you have some reference sheet explaining all symbols and some basic calculations. You have the log, analysis log. We'll make it a little bit smaller. You have the population parameters, the patient data, patient analysis, and of course these fits again. So I'll make it smaller, have a nice overview of the individual fits. And the simulation data. Okay, so I will close the output of the Excel again, and I will now continue. What I can do now is, for instance, I can reset it to the original values. I click here, reset, and I see the original starting values are restored again. And what I can show you now is a new setting we added here in the setting screens. And it's called parallel processing. So what we had in the past is that we had sequential processing. So if I can simulate it again by unchecking this option. And we also had updates with each iteration, fit iteration. So now if I recreate the old settings in the previous version, and I go to the fitting screen again and start the fitting, you see now that the patients are fitted one by one in sequence. And if there are some patients that I have trouble fitting, it will hold up the whole process, of course. So after 4 cycles, it has been completed. And you see it takes longer, of course, because those difficult patients may hold up the whole process. And so let's reset it again, and I'll go to the settings screen again. So I will simply set the old settings again with the parallel processing. You will see it goes much faster. And on my machine here, I have a Intel i7 with 4 cores, and each core has 2 threads, so I have 8 threads. But you can really benefit from machines with multiple cores. And for instance, a modern workstation with a Xeon processor, you can have up to 20 or even 40 cores in a dual processor configuration, and then you can really speed up things. So this concludes the presentation. I hope you liked it, and thank you for your attention.